Okay, so welcome to the second lecture. First, maybe I will make some brief summary of what I said last lecture. So I was talking about representation theory of finite groups. So basically, if you have a finite group G, and you are looking at the complex finite dimensional representations, then if you have such a complex representation, then the space of the representation can always be decomposed into a direct sum of irreducible representations. So each of these spaces will be invariant under the action of the group. Okay, it will be invariant subspace, and so for each G, so the restriction of rho of G to Vi. So this gives me something which I can view as an element in the linear group of Vi. And so this will be a representation of the group G. And so I can always do such a decomposition where the Vi are irreducible representations. Okay, so by restricting with the smallest possible subspace that I can find, which are invariant in some sense. Okay, there is always such a decomposition. And in order to find, if you are given the representation, in order to find the Vi which occur in this decomposition, their list is unique. It's completely determined by the decomposition, by the representation. And the recipe to do that is to look at the character of the representation, this function. If you look at the trace of this representation, then of course it will be the sum of if I take the trace of an element, it will be the sum of the traces of this element on the invariant subspaces. So it will be a sum, okay, like that. And if you want, I can maybe write this like that. Because in this list, some of the representation may be equivalent. And as I said, if I consider representations, then two equivalent representations have the same character. So then if I can rewrite this as a sum of all irreducible representation, say, let me call, for example, G hat the set of irreducible representation up to equivalence. And then you can write this sum as a sum over all the characters. It's a linear combination of all the characters which are irreducible characters with some multiplicities, which can be non-negative integers. Okay. And there is, of course, a finite set here. It's a finite, everything is finite. And we have this sum. And as I said last time, so these functions form a basis of the set of functions which are invariant by conjugation. So certainly, everything is completely determined. So this function, it is just its expansion into this basis of a function which are invariant by conjugation. Okay, so we have this. So now the goal of representation theory, if you are given a finite group, is to understand all the irreducible representation, which form in some sense the atoms of the theory, the things that you cannot break into smaller components. And given, and then a very important thing then is to be able to compute the characters, because then if you are given an arbitrary representation, then you will be easily able to decompose it into irreducible representations. Okay, so this is what I'm going to explain today. I'm going to explain how to do that for symmetric groups. Okay, how to find the irreducible representations. And I will try to give as explicit as possible description of the irreducible representations of the symmetric groups. And well, I will give you some hints of how to compute the characters, but there are more. I will not give you the most efficient formulas because it will lead me too far. But actually, I will explain to you how to essentially build the representation of the symmetric groups. Okay? So for that, we need to introduce the symmetric groups. So I will denote by Sn the symmetric group on a set of an object. So the first thing is to understand what are the conjugacy classes. Well, I think everybody knows that if you have a permutation of n objects, then you can always group the objects into cycles. And the permutation goes along cycles. You have a disjoint. You may have some fixed points, okay, like that, and okay. So this is a typical permutation, and if you put arbitrary labels on the vertices of this graph, consisting of cycles, you build an arbitrary element in the conjugacy class of this permutation. So it's a conjugacy class, and the conjugacy class, of course, it is completely determined by the length of the cycles, and you can give the list of the length of the cycle into decreasing order, and it gives you a partition. Okay. Of course, n. These are just the orbits, of course, of the permutation, etc. Right, so it's a list which is finite. Or if you want, sometimes it's also nice to consider it as an infinite list, which is 0 after some time. Okay. So these are the conjugacy classes, and as I said last time, it's convenient to draw a conjugacy class to represent it by a picture like that, where you give the list. So each row here consists of lambda, say lambda 1 in the first row, lambda 2 in the second, and so on. So you have a list of, and as I said also, I will represent them. Usually I will use this picture rather than this one in order to represent the conjugacy classes. Well, this will not represent the conjugacy classes, actually. This will more be related to the irreducible representation. As I said, there is the same number of both, so, but it's not obvious for a general group how to index the representation by conjugacy classes. But in the case of symmetric group, there is some quite canonical choice for doing that, and I'm going to explain that now. Now some geometry. We are going first to do some geometry of the symmetric group. Okay. So as I said, when you do representation theory, basically you are trying to do Fourier analysis on the group. So we will use, of course, the group law, because this is just the only thing we have about the group. It's law. And so we have to understand how to multiply elements in the symmetric group. This is a very difficult subject. I mean, multiplying elements in the symmetric group and trying to understand this multiplication, it's not easy. And certainly, I mean, for example, people who know maps know that there is a close connection between products in the symmetric groups and maps. Okay, some classes of maps can be expressed in terms of factorization inside the symmetric group of some elements in the symmetric group into other elements. Okay, so there is some geometry here. And so we will start with the simplest elements of the symmetric groups, which are apart from the identity, of course, which are the transpositions. Okay, so a transposition is just, it corresponds to the partition where you have lambda 1 equal 2 and the other equal 1. It's just a transposition. It exchanges two elements, I and j, and leaves the other fixed. And now we are going to look at the Cayley graph of the symmetric group and letters. The first thing is that the transposition generates the group, the symmetric group Sn. And using that, you can build a graph, a connected graph structure on the group Sn by saying that there is an edge from sigma to tau if, say, sigma tau minus 1 is a transposition. So let me call T the set of transpositions. Okay? And of course, this is equivalent to tau sigma 1 being a transposition. So this graph is symmetric. Okay? You can consider it as an oriented graph. In general, if you have a group and a set of generators, you can always build this Cayley graph. But here, because the transpositions have these properties, and it's asymmetric, so we don't really use here the oriented structure of the graph. So it's a graph on the symmetric group, graph structure. Well, for S2, it is just you have the. It's very simple. For S3, it's slightly more involved. So near the identity, of course, the next nearest neighbors are always the transpositions. And then you have the two cycles, 1, 2, 3, and 1, 3, 2. Okay, when I write permutations, I usually write them. There are two ways to write permutation in general. It's one way is to, if you say, for example, you are looking at permutation of one end, you just list the numbers as sigma 1, sigma 2, etc. Or you can write them as a product of cycles. And usually, I will prefer to use here the product of cycles. It depends on what property of permutation you are interested in. But for what I'm doing, it's better to write them as product of cycles. So here, I mean the cycle 1, 2, 3, like that. Okay. In general, so when I write that, and if I have several disjoint cycles, then I write the product. Okay. So here is the graph, and there is a distance associated to this graph. So what is the distance? So because the transposition form a conjugacy class, actually, you see that the distance is something which is very, very invariant by conjugation. So the distance between, say, sigma and tau is the same thing as the distance between sigma tau minus 1 and the identity. And actually, it depends only on the conjugacy class of. So if I this is a length actually, a length function. That means that this function satisfies the properties that the length of a product sigma tau is always smaller than the length of sigma plus the length of tau. Okay. So we have a distance on the graph, which is induced by some length, which is here. And this length actually depends only on the conjugacy class of the element. So what is the length of an element? In order to understand that, we have to understand how to multiply permutations, or how to multiply a permutation by a transposition. And, OK. So let us see what happens. So suppose we start with a permutation with some cycles like that. Okay. So suppose I have a few cycles. Maybe we have to rearrange them in order to specify the permutation. We have a cycle, and we want, so this is my permutation sigma. So what happens when I multiply sigma by ij? So I want to find the length of sigma. So I want, in some sense, to find so this length. So it is the distance of sigma to the origin. So it is the smallest k such that sigma can be written as a product of k transpositions, okay, by definition. Definition of the distance in the graph. When you go along an edge in the graph, you just multiply by a transposition. Okay, so what is it? So what happens when I multiply sigma by a transposition? Well, there are two possibilities. I have to find where the I and the j are on the graph. So maybe say I is here, so where is j? So there are two possibilities. Either j is in the same cycle as I, okay? And then what happens is that in the new permutation, which is here, so you see I is mapped to j, and then j will be mapped to some other things. And then, okay, so this is what happens. And okay, now I have to take the composition, and it will give me a cycle like that in the group. And j is mapped to A, which is mapped to this point. So I have a cycle like that. So here, in my new permutation, I have a new permutation with two cycles. So the cycle has been broken into two pieces. Okay. So there is one more cycle. And the other possibility is that I and j belong to two cycles. Okay. Then what happens? So you map I to j first, and then to its image. So the new permutation goes like this, goes from I to the image of G, and then it goes around like that, okay? And then you arrive at this point here, and this point, so, this point which is J, and now J, it is mapped to I, which is mapped to this point here. So if you do that, then you arrive here, okay? And then you go around, etc., until you meet J, okay? So what you have done is you have built a new cycle, which is the union of the previous cycles, okay? The other possibilities, there is one less cycle. Okay, so each time you multiply, you have two possibilities. Either you merge two cycles into one, or you break a cycle into two, okay? And so you see, if you want to find the shortest path to the identity, then the identity is the permutation which has the largest number of cycles. It has exactly n cycles, n orbits. So if you want to find the shortest path, the things you have to do is that you have to add cycle. You have to break a cycle at each step, okay? And it's clear that you can do that because if you have a non-trivial cycle, you can always break it by taking two elements in the cycle and multiplying by the corresponding transposition, okay? So finally, what is the length of an element, sigma? It is n minus the number of cycles of sigma, okay? So for example, for the identity permutation, it has n cycles, so the length is 0. And so what are the elements which are the longest elements in this using for this distance, I mean, for this length function? The longest elements are the ones which have the smallest number of cycles, so they are the full cycles, okay, in particular. Longest elements. So they are what I call the full cycles, the cycle on cyclic permutation on n elements. Okay, they are the longest elements. And now an interesting question is, well, we have seen that the longest element are these, and we may ask, there is this element here, there is this longest element, so in how many ways can we go from this cycle from the identity to this cycle by multiplying by a transposition by the smallest number of. So exercise, prove that. So let me call Cn a cycle of length n. So sorry, it will be of length n-1, so it will be a full cycle. Prove that Cn, so I can write it as a product of n-1 transpositions. Yes? Oh, it's a number of cycles. That's the number of cycles. And the full cycle is the one which has only one cycle. It's a permutation with only one cycle. Oh, there are many of them, but okay, choose one. The length is always n-1 in this when you use this length function. So certainly you can always decompose such a cycle into a product of n-1 transpositions. So how many? So Cn has, so it's n-2 decompositions into n-1 transpositions. So product of n-1 transpositions. So it's an exercise. And now I make some simple remark about this. So what is such a decomposition? If you look at such a decomposition, so Cn, so you can look at the set of intermediate permutations that you obtain. That's T1, T1, T2, T1, T2, T3, etc. The ones that you obtain when you do the product. So these intermediate permutations, they are on a path. That's the one that you obtain when you choose a path which goes from the identity to your permutation, to your full cycle. Okay? And so they form a particular. So here, for example, for n equals 3, you have these 3 paths, which are here. So that's really 3 to the 3 minus 2, it's 3. You can check the result in this case. And okay, so there is here something very important because later on we'll see that when we will do asymptotics, we will see that free probability comes in. And in free probability, there is something which is very important, a notion which is very important from combinatorics, which is the notion of non-crossing partitions, which are some kind of planar maps also. And, so it's something very important in this theory. And here we will see we can see them appearing very naturally for the following reason. So let me draw a picture. So here is a full cycle, Cn. Okay, like that. Suppose, for example, I go in this way. Okay, so if I want to draw so let me go in the reverse direction. I start from Cn, which is the last one. And I multiply on the right by Tn minus 1, then Tn minus 2, etc. So what happens? Well, first thing I do is that, as I said, I just break the cycle into 2 cycles. Okay, so this gives me my permutation Tn minus 1. Okay, then what I do if I want to multiply by a transposition and have another cycle, then I just need to break one of these 2 cycles into 2 cycles. So let me assume, so for example, I do that. And then I get a fixed point, okay? And okay, and I continue like that. Next step, maybe I will draw another cycle. I will break another cycle like that, and so on, okay? So what do we get as intermediate steps? What we see is that the intermediate steps are always what are called non-crossing partitions. So what is a non-crossing partition? So let me call my elements 1n. So I choose an order, but it will depend only on the cyclic order on 1n. So a non-crossing partition of 1n, it is a set partition of this 1n, such that if you draw the partition, so if you have a partition, then if you have a part in the partition, you can always draw the polygon, the convex polygons. If you put the endpoints on a circle like that in regular order, you can always put any partition at, you can always draw the convex polygon, okay? And the partition is called non-crossing if all these polygons do not intersect, if you draw them on the circle like that. And if you want to write that in a non-geometric way, but more in a more algebraic way, so it means that there does not exist AJKL. There is no crossing. That is, there is no, say, 4 elements such that I and K are in the same block of the partition. J and L are in the same block, and the 2 blocks containing these numbers are different. And okay, if I write here, I just mean that these 2 numbers are in the same block of the partition. Okay, so this means if you draw the partition on a line like that, up to n, this means that you don't have such a configuration like that. Okay, if you write each time you draw an arc between an element I and the next in the same block, okay, you cannot have such a configuration, which is a crossing. Okay, so we see there is a bijection between the non-crossing partitions and the permutations here that are on a geodesic between the identity and the full cycle. Okay, so I can make this geometric remark here. It will be very important in to have this non-crossing partition, but later on. But I make the remark now. So non-crossing partition correspond bijectively, so say of 1n. So permutations on a geodesic. A geodesic is a path of minimal length between the identity and the full cycle in the symmetric group, Cn. Okay. If you choose the cycle from 1 to n, you get this picture. Of course, if you choose another cycle, you just have to renumber the points according to the order in which they appear in the cycle here. Okay, so you can say also that they satisfy this equation, which is here. Okay, okay, so we have a geometric interpretation of the non-crossing partitions using this the Cayley graph of the symmetric group, which will play an important role in the sequence. But for the moment, okay. So another thing that we have seen from that is that the length function is important in the symmetric group. So now, if we have, so as I said, there are many decompositions of a permutation into a product of transposition, even many which are of minimal length. But there are some which are canonical. So for example, take a permutation sigma. Yes? the length of Cn is n minus 1. That's the number of transposition you need to express Cn as a product of transposition. No, sorry. It was from my previous. I didn't erase that. Okay. No. Okay, so if some permutation sigma satisfies this equation tells you that you have equality in the triangular inequality. Okay. Usually you have this. Okay. Usually, as I said, the length function satisfies the triangular inequality. But here, when you have equality, okay, then this means exactly that your permutation here, or this permutation also here, is a non-crossing partition. Okay, so we have this geometric way of understanding this geodesics in the symmetric group, if you want. Okay. So now, let's go on. So suppose you have a permutation sigma. And so there are two possibilities. Either n, sigma of n equals n. Then sigma belongs to Sn minus 1. OK. Here, I'm assuming Sn is really the set of permutations of 1n. So Sn minus 1 is the set of permutation of 1n minus 1. So, and I consider all the symmetry groups as embedded into one the other by the obvious embedding. Okay, and or maybe sigma of n is different from n. Okay, so in this case, you can write sigma is sigma prime times some in, some permutation of the form in, where sigma prime is in Sn minus 1, and I is unique. There is a unique such decomposition. Okay? And moreover, so as you see, this means that your n is here. Then this means that this new permutation, sigma prime, will leave n fixed. So this means that in your permutation, so I think I should be maybe sigma of, yes, it's I is here, sigma 1 of n. Okay, that's the antecedent of n in the permutation sigma. Okay, and if you do that, so the new permutation, sigma prime, is the one that you obtain like that, but just jumping above n, and n will be given by that. Okay. So you just do this simple thing. OK. And so what you see is that we have one more cycle in sigma prime than we had in sigma. So this means that the length of sigma prime is smaller than the length of sigma by 1. OK? So from this simple consideration, what we see is that we can write down the generating function for this length function. The length function, which is L, which is here. So the sum of a sigma in Sn of L, so I will use Z L of sigma times sigma. So this is a generating function inside the group algebra of the symmetry group. So this is the sum for sigma in Sn minus 1, sigma prime in Sn minus 1, Z to the L of sigma prime times identity plus the sum of in, Z times the sum of in. Okay? This is just the translation into algebraic terms of the computation that I did here. Okay? And I can rewrite this as, OK, then, so let me give a name to this object which is here. I will call this Jn. So Jn will be the sum from I equal 1 to n minus 1 of the transposition in. Okay? So it is a sum of transposition, which means that we are in the group algebra, the algebra generated by the group. Or maybe if I use a notation that I were using, but I should maybe call it this. I should call this delta in, the Dirac measure at IN if you want to talk about the group algebra. Okay, so this is an element in the group algebra. And we see that, if I look at this sum, it factorizes here. And on the left, we have the same sum, but considered in the group Sn-1. So this means that I can iterate this factorization. And in the end, I got the product from I equal, say, 2 to n of E plus Z Gi. Okay? And this is the generating function inside the group algebra of the length function on the symmetry group. Okay? Now there is a little ambiguity. I put here a product. But we are in an algebra which is non-commutative, so we must be careful about the order in the product. But notice something. It is quite obvious. Remark. Jn commutes with the sigma prime in Sn-1. It commutes with all the elements in the algebra Sn-1. Why does it commute? Well, you see, if you try to compute this, you conjugate Gan by sigma, where sigma, or let me call it sigma prime. Sigma prime is an element which doesn't move the element n. Then if you do that, you see that you are just permuting the elements in the, because if you this will be some Jn, where J is I don't know if it's sigma prime I or sigma prime minus 1I, but okay. There is some J. So what you are doing is you are just permuting the elements in the sum, okay? So this proves that this is equal to Jn, actually. It is the same sum in the different order, okay? So this means that Jn commutes with all the elements in the group Sn-1, so in particular with all the elements in the algebra generated by Sn-1. So this proves, in particular, Jn commutes with all the Ji, that's where I is smaller than n. So this proves that, so this means by induction that the Jn, they all commute. Okay? So in this product, since the factors commute, there is the identity and the Ji. So the Ji generate a commutative algebra. Okay, they all commute. So there is no ambiguity in the product. Okay? You don't have to take it from left to right. Actually, it doesn't matter. You can do whatever you like. Okay? Now these elements are very important. They will play a very, very important role in what I'm going to say. And they have a name. These elements are they are called the. So I'm sorry, I'm not Russian. I don't know how to speak Russian. So I think it's pronounced something like Yuchish. But if I do it, if it's wrong, what? G, J, U, c'est un C, Y, and S. What? What? Oh, it's Lithuanian. Okay, okay. Okay, it's Lithuanian. You know that. Okay. I don't know. Anyhow, it's not, I don't know how to pronounce it, so I will just say Uchis Murphy element, and hope you understand what I mean. Okay. Okay, they are called the Uchis-Murphy elements. So they are elements in the group algebra of the symmetry group. And it turns out that these elements I'm going now to use in order to describe the irreducible representation of the symmetry group. And for that, I will use these elements in the group algebra of the symmetry group. Okay? They will play a very important role. As you see, they play an important role in understanding the connection between the geometry of the symmetry group that encoded in this length function and the algebra of the symmetry group and we see here that really the Justice-Murphy element play an important role here, and they will it is really these elements which will allow us to make the bridge between the combinatorics of the symmetric group and the algebra, that is the representation theory of the symmetric group. So that's, okay, that's where we will leave the general theory of representation to really enter the representation for this specific group. And this element will play a fundamental role. Okay, so what I'm going to explain now is a theory that was, so these elements were introduced in the 70s by, I think independently by Duchis on one hand and Murphy on the other. And well, they were interested in the following remark, is that if you look, okay, you can rewrite this like that, where here you write the elementary symmetric functions in the J's, okay? If I imagine the J as the root of your equation, so you can always write the elementary symmetric function in the J. So what we see is that the elementary symmetric function in these elements, J, they are the sum of all sigma in the symmetry groups of Sn, such that the length of sigma is equal to, so it must be, I think, k. Let me see, it's k. It should be equal to k, I think. Yes. Just k. Okay.
What is the index of
J? J. So it is elementary symmetric. So I have n-1 elements, and I can always. Okay, they start from 2 actually. They start from 2, and so say J2 is equal to 1, 2. J3 is equal to 1, 3 plus 2, 3, etc. Okay? So the index here refers to the largest element which appears in every transposition that I have here. Okay? So in particular, you see these, you have these elements here, and these elements are, so I sum all permutations which have the same length, and it is given by an elementary symmetric function computed in the Gersich-Murphy element. And well, if so it's well known that these elementary elementary symmetric functions, they generate the algebra of all symmetric functions. So if you take any symmetric function in the J's, you will get an element which can be expressed so it will be expressed as a polynomial in these things. And okay, so now I will make a little digression because I want to explain something, but it's better to explain it more generally. So about the center of the group algebra. So what is the center of the group algebra? Suppose you have a finite group, J. So as I said, you can take a linear combination of elements in the group. So this is an algebra, generally a non-commutative algebra. So the center of the group algebra, well, it is the center. It is a set of elements in the group algebra which commute with all the other elements. Okay? And so there is a basis for the group algebra, the set of elements for the center of the group algebra. For each conjugacy class, C takes the sum of the elements in the conjugacy class. Now this element commutes with all elements of the group, so it commutes with all elements in the group algebra. So it is in the center. And actually, it is very easy. Take any element in the group algebra. Then the sum over G of G, M, G minus 1, belongs to the center of the group algebra. Okay? If I take any element, which is a linear combination of the elements in the group, then this sum here over J commutes with all the elements in the group, because when I multiply by some element, okay, I can move the multiplication by resumming to the right. So it's an elementary computation to see that this is always in the center of the group algebra. So in particular, this, if you decompose M into a linear combination of elements of the group, this element will be a sum of elements of this form. Okay? So this proves that these elements here, they generate the center of the group algebra. Okay? They form a basis of the center of the group algebra when you are over all conjugacy classes. Okay. So an outcome of what I said last time is that we have another, there is another basis. So this basis is form of the linear combination of elements in the group algebra, where the combination is given by a character, an irreducible character. Okay? So this is another basis, so this belongs to the center group of the group algebra because this function, chi omega, is invariant by conjugation. Okay? So certainly this is a linear combination of elements of this form. Okay? And it turns out this is part of the representation theory I was talking about last time, that they form a basis, another basis. Of course, we know that there is the same number. Okay? So here we see that all these elements here, they belong, they are sums of conjugacy classes, because you know that the length of an element depends only on the conjugacy class of the element. Okay? So here, this really is invariant on the conjugation of this element. So it belongs to the center of the group algebra. Okay? And now the point of what Judges and Murphy did is that they proved that actually taking polynomials in these elements, you can take arbitrary symmetric functions of the J's, and you can get all the center of the group algebra, of the symmetric group algebra. Okay, so the theorem by Justice and Murphy, independently, is that the Z, so the center of the symmetric group algebra, is included in the polynomial, actually is equal to the set of symmetric polynomials in the GIs. Okay? Take symmetric polynomials in the GIs. I showed you that they are actually in the center of the group algebra, but actually the converse is true. Any element in the center of the group algebra can be expressed as a symmetric polynomial, so actually as a polynomial in these elements. Okay, this is not very difficult to prove. What is difficult is to think that it's true. But once you have thought that it's true, it's not very difficult to prove. I'm not going to prove it now, but I'm going to show you some other similar results that from which you will be easily able to find a proof of that. I mean, it's not very difficult. Right. Yes. No. Every element can be, there is an inclusion, obvious inclusion from what I said. And what I say is that actually there is another inclusion, that everything can be expressed as a symmetric polynomials in the Justice-Murphy element. No, of course. There is infinitely many polynomials. It's an infinite dimension. The set of symmetric polynomials is the infinite dimensional space, so you cannot expect, certainly there are relations between the GIs. It's a symmetric polynomial in the GIs. So that's the image of the symmetric polynomial into the group algebra when you substitute the GI for the variables. That's what I mean. So, okay, of course, everything is finite dimensional here. Yes, certainly we will see more of that, okay? We will use a lot of such kind of things, yes, certainly. Well, actually, for example, it's a very interesting question to express the characters, which are elements in the center, as polynomials in the Cauchy-Murphy elements. Okay, that's very interesting. Or even the conjugacy classes. I mean, you have two bases, which are the conjugacy classes and the characters, and both of them can be expressed into symmetric polynomials in the Cauchy-Murphy elements. So maybe to tell you that if this is really not very difficult, I just show you the beginning. So we have the sum of the GI is just the sum of the permutations. Okay? So it is just the conjugacy class of all transpositions. Okay? Now the sum well, no, it's a bit, I don't, okay. Yeah, the sum of the GI Gj, it is the sum of all elements of size 2, of length 2. And for that, I have the okay? So this is the sum of all transposition of all products of two disjoint transpositions. Yeah? Or maybe, yes. Okay. Okay, I don't care. Maybe there is some factor. Okay, here probably I have to count them twice. Yes, each. No, sorry, no, it's no because there are some conditions. No, it's not. Well, I don't know. You. What?
On the left, you put the index I.
Oh, okay. Sorry. It's U and V. Okay. No. I think it's no. It's there is no. No, as I said, this is the identity actually. So it's just. I just count all this permutation of this form in this conjugacy class, and it is a sum of two conjugacy classes. What I say. Okay. And now you can do something else. Take the square of the first one here. The sum of the GI square. And now what you see is that you will get, well, you will get some, so it is the square of the conjugacy class of transpositions. So you will get n minus 1 over 2 times the identity, because the square of each of this transposition is the identity. And you will get a linear combination of this and this, okay? Because all this can be obtained by taking a product of two transpositions, okay? And exactly by the number of ways you can write it as a product of two transpositions, okay? And I think you will get 2 sigma of ij kl plus sigma of ijk. Is it right? No, it's. I think it's 3 here. Okay, because there is. Yes. As I said, there is exactly 3 ways of decomposing this cycle into a product of two transpositions. Okay? So we see we have 2 linear combinations here of these 2 classes, but by making linear combination of these elements, we can find this class and this class, express them as linear combination of the elementary symmetric. And okay, it becomes more complicated when you look at higher powers, but I mean it's not very difficult to see that you can go along these lines further. I mean, it's a combinatorial exercise. And if you are interested, you can try to do it. Okay. Okay. So where was I? So I was. So these are the Cauchy-Murphy elements. They will play a very important role. Okay. And okay. So now I'm going to describe the representation theory of the symmetric group using these elements. Okay. For that, I need first to do some complements to what I said yesterday, not yesterday, Tuesday, on the general theory of the. For this, I need to analyze something, which is, I assume I have a group G. So I look at the group algebra, CG. So I described here what is the center of the group algebra. Okay, so maybe it's a so as a vector space, of course, this CG is the same vector space as the L2 space of G. Although when I look at CG, I see it as an algebra, but here I looked at this rather as a space on which the group acts, on the left or on the right. You remember that I had left and right action. And I had this decomposition. Okay, and now I have a similar decomposition of the algebra CG. It is a sum, so omega, the irreducible representation. And here I have V omega tensor V omega hat, but here I want to interpret this as a matrix algebra of, say, the endomorphism of V omega. Okay? And now this is an algebra. Okay? And this is a decomposition into algebras, direct sum of algebras. What does this mean concretely? Concretely, this means that if you let me write down a matrix. So if I have a suitable, I can choose a suitable basis of my space L2G. Into I have this decomposition. And if I look, say, at the left representation of the group algebra G, then this left representation will be decomposed into, I can decompose my space into smaller blocks, like that. So I will have smaller blocks, one block for each omega. Omega will be irreducible representation. And each block will be decomposed into smaller blocks. Okay, like that. So, and so there is so if I choose this decomposition of L2 of G, any element of C of G will appear as a matrix like that. And in this matrix, so as you see, suppose that the dimension of omega is some number, say it's 3 here, then the multiplicity of omega is equal to 3 here. This means that here, when I represent my matrix, the matrix of an element, G, it will appear 3 times here. So let me call the image of this element in the different representation as A, B, C, for example, C. Okay, so this will be, say, for example, a 4x4 matrix, if in this case where I have, because it is a dimension of the representation, but it is also the multiplicity of the representation. Okay? Yes? A sum before?
Direct sum of n of
Yes, yes. Yes, what I mean is that, actually, inside the sum, there is an isomorphism inside the sum. As I said yesterday, if you take a vector space and you tensor it with its dual, it's isomorphic to the endomorphism of the, it has a natural algebra structure. And it is this decomposition, okay. Yeah.
For example, A, we should consider it as
A will be a matrix, and the size of the matrix will be equal to the number of times it appears.
Yeah,
it's 3 in this case, and maybe it's alpha here, it will be just a trivial representation or whatever, okay? But anyhow, you can, this decomposition in concrete terms means that you can decompose you can find a basis of your space in which you have all the matrices of the representation will look something like that, okay? And so you will have multiplicities. Huh? So and you see that the algebra, for example, the algebra generated by this piece here, it will be exactly the endomorphism of this space, and each one will appear a certain number of times. Okay. Now, what is the commutant of this algebra? The commutant of this algebra inside itself is just the center of the algebra. So we have to distinguish between the commutant in itself, which is the center, or the commutant is the larger algebra, which is here. And we see that for example, so if we want to find the commutant of this, of all these operators generated by all these matrices, then we see that, for example, in this algebra, we will have all. So maybe I should call Schur's lemma. So suppose is irreducible. So I take an irreducible representation. Suppose that A belongs to GLV, and A commutes with all the operators rho of G. It commutes with the representation. Now take any eigenspace of A. So we are over the complex numbers, so there is at least one eigenspace of, we can find at least one eigenspace of the matrix A. Then this eigenspace will be invariant under the action of the group. It will be an invariant subspace by the action of the group. But if I assume that this is irreducible, then this invariant subspace may be either 0 or the whole of the space. So this means that A is a multiple of the identity. Okay? Any operator which commutes with the group, the operation of the group will be a multiple of the identity. Okay. And now one can see that this implies that, in fact, the algebra generated by all the rho of G, they are the commutant of this, but so it's all the set of operators. Okay? So the algebra generated by the representation, in this case, it is the algebra of all endomorphisms of V. Okay? So now when the representation is not irreducible, you may have many operators which commute with the representation. For example, here the representation is decomposed into irreducible representation. There are sums of, but here we have identical representations. So you see, if I take a matrix like that, in which in each of these blocks, I put a multiple of the identity matrix, say alpha 1, 1, alpha 1, 2, alpha 1, 3, etc. Okay, I put the alphas are multiple of the identity matrix. Okay, then this matrix will commute with this matrix, which is diagonal, made of block diagonal matrices, which are identical. Okay, so this means that the commutant, and okay, so what one can show is that these things you can do in every block, which is here. And in every block, you will have some matrices like that, so beta 1, 1, beta 1, 4, etc., which are in each block, which is decomposed into subblocks, I put a multiple of the identity. Okay, and this will commute with this matrix. And actually, one can show that this is exactly the commutant, the operators of this form, which has this form of diagonal blocks. They are exactly the commutant of this. So, yeah. Yeah. It's that all the operators which commute with some family of operators. So, yes, okay. So if S is a set of operators, then usually it's called S prime. S prime is a set of all, say, T, such that St is equal to Ts for all S in big S. Okay, that's the commutant. And so, now let me take another, an arbitrary a representation of a group, a finite group, GLV. So suppose this representation is decomposed into irreducible. So this means that I have, okay? So this means in general that I will have blocks. Etc. And in each of the blocks, so in each of the in each of these, so there is a power here. This means that this vector is repeated. There is a tensor not a tensor product, a direct sum of m omega copies of these elements. So this means that I will have the same picture here. I will have, but here instead of having the multiplicity which is equal to the dimension, it will be an arbitrary number, m omega, which can be 0 or a positive number. Okay. So this is a general representation of the, it can be decomposed into different, so here the sum is over all the distinct irreducible representation of the group G. You can describe it like that. And now, if I look at the endomorphism, so the group, say if you want the image of the group algebra, that is which is the same thing as the algebra generated by the representation, inside this endomorphism algebra, it will be isomorphic to the sum of matrix algebra. Okay. And now, if I look at the commutant, it will be a sum over omega of matrix algebras of the dimension, the multiplicity. Okay, because you see for each omega, so here I have some multiplicity. Okay. And so for each of these blocks here, I will have in the commutant, exactly like that, I can put in the commutant arbitrary matrices made of blocks of multiple of the identity. So the commutant will be a sum of matrix algebras like that. Okay? And now a very important consequence. Any representation. Any representation, you can write it. Okay? So in general, this algebra is a sum of matrix algebras. It is a direct sum of matrix algebras. Okay? When you look at a representation of this algebra, some of the the matrix algebras are things which are very rigid. If you want to find a representation, linear representation of a matrix algebra, the full matrix algebra, it is either 0 or a matrix algebra. This means that when we try to represent this algebra into some vector space, then some of the omegas will be cancelled because they will appear with multiplicity 0. And the other which appear with multiplicity larger than 0, they will be mapped to they will be just mapped by the identity representation or by an isomorphism representation. Okay? So this is some basic fact about representation of algebras, of matrix algebras. Okay? And what we see is that the multiplicities, they appear from looking at the commutant of the representation, that is the endomorphism which commutes with the representation. If we understand the commutant of a representation, then we can understand the multiplicities. Okay, the commutant of the representation will be a sum of matrix algebras, and the dimensions which appear in the matrix algebras are the multiplicities of the irreducible representation. Okay? So this is the structure of a general representation, and its commutant reveals a lot about the structure of the representation. Of course, if you look only at the commutant, you get these numbers, but you don't know to which omega belongs the multiplicity. This is something you cannot tell just looking at the commutant. Okay? And you know that there is some index set omega, and there are some multiplicities, but you don't know how to relate them to the representation if you just look at the commutant, because the commutant can be the commutant of many, it's commutant of an algebra, but it can, the algebra can come from many representations, and there is no reason you should recognize your group from that. Okay? Yes? On fait une pause? Il est quelle heure là? Okay, maybe a 3-minute break. Okay, so now I'm going to explain how to build the irreducible representations of the symmetric groups using these elements that we have just seen, the Joshis-Murphy elements. Okay, so as I said, Jn, the basic observation is that Jn commutes with Sn-1. Okay, so this is the first observation inside, inside the group algebra. Sn. Okay. So we have an element in the commutant of an algebra. That means that we have a way to understand something about the multiplicities of if we take a representation of Sn, we restrict it to Sn-1, we have a way to understand the multiplicities using this element. Okay? And actually, we have a very good way because of the following lemma. The commutant of Sn-1 in the algebra C of Sn. So this means that all the elements in the group algebra of Sn which commute with the elements of Sn-1. So this commutant is generated by so on the one hand, the center of Sn-1. Certainly, this belongs to the commutant of Sn-1 because elements of the center, they commute with all the elements of Sn-1. It is generated by also Jn, and that's all. Okay, so this is the basic observation that these these elements, the center of the group algebra of Sn-1, and the Joshis-Murphy element, which does not belong to Sn-1, it is the only thing you need to add to the center to get the whole commutant of the algebra. And this is really the basic fact. And what is very nice is the following, is that we know that Jn commutes with this, but so it commutes also with this, a fortiori. And so this algebra is commutative. So the commutant is a commutative algebra. This is very important because in general, we know the commutant will be a sum of matrix algebras. But since the commutant is commutative, all these matrix algebras will be one-dimensional algebras. Okay? So this means that all the multiplicities will be equal to 1. Okay? Consequence, so I write it. All multiplicities. So I will explain in more detail what it means, but let me note it before. All multiplicities of representations of Sn-1 inside Sn will be so 0 or 1. Okay, I come back to that in a minute. But first, we need to check the lemma. Why is it true? Okay. Well, certainly, we know that the commutant contains these things. Okay, so we need to prove the reverse inclusion. So now there is a simple description of the commutant of Sn-1 into Sn. What is this description? So suppose that M belongs to the algebra of Sn, then I can build an element which commutes with all the elements of Sn-1 by looking at, say, the sum of G, M, G minus 1, say, belong to the commutant. I denote the commutant by a prime here, okay? So it is the commutant. It belongs to the commutant of Sn-1, okay? So this operation, if you want, you can even divide by the number of elements of Sn-1 here. This is a projection, okay? This operator is a projection because if M already belongs to the commutant of Sn-1, then all these terms are equal to M, okay? So this operation maps any element in C of Sn to an element in the commutant of C of Sn-1. And it is a projection. It is a surjective projection because any element which already belongs to the commutant is mapped to itself by this map, okay? So I know that I can, in particular, if I take just M to be a permutation, permutation of Sn, I get an element like that in the commutant of Sn-1. And these generate, they form a generating system of the commutant, okay, by what I just said, okay, because M can be always written as a linear combination of the sigma, okay? So now, so of course, these contain, in particular, if sigma already belongs to Sn-1, this is just the sum in the conjugacy class, okay? It is an element in the center of Sn-1. So these elements, I say, they are here, okay? So now, there are the elements where sigma does not belong to Sn-1, okay? Suppose sigma is some permutation. So this means it will be a product of cycles, a product of disjoint cycles like that, okay? And my hypothesis is that it does not belong to Sn-1, so it belongs to Sn. So the n must be in one of the non-trivial cycles, say it is in here. I can always put it in the n by just using the cyclic permutation. Okay, so there is, so this means that sigma can be written as a product of cycles like that. The n is in one of the cycles. Okay. And now what happens when I do all this conjugation and I sum? Well, I will sum over all elements where here I put arbitrary numbers between 1 and -1. Okay? I will have the sum of all of these. Maybe some of them I will get several times. Okay, but certainly I will have the sum of all of these here. So I may have some several times because I may have cycles of the same length which appear here. So the action here may not be. Okay? So how can I parameterize the different sums that I get here? So for that, I need a partition of n, which gives me the conjugacy class of sigma, okay? Because all the elements here will be conjugated, but not all the conjugate of sigma will appear here. Only the ones in which n is always in the same cycle, the cycle of the same length, okay? So this means that I can parameterize sigma by, say, some Young diagram like that. But in this Young diagram, I have to say where, in which of the parts of the partition is my n, okay? And, okay, so this is what I call a marked partition. And moreover, if some partition appears with, some part of the partition appears several times, I can always assume that I mark the first one here, because, of course, if you have in chi L or chi L in, it is the same, of course, the same element in the symmetry group. So I can, if you want, I just need to mark one of the lengths of the partition of the parts which appear in my partition. Okay? And when I do that, I get a parametrization of all the elements of this form that I can form. And I know they form a generating system for my elements in the commutant of Sn-1. Okay? Well, now, what do? We have to prove that all these elements can be obtained using the center of Sn-1 and the Gn. Okay? So let us start. So what is Gn? Gn is exactly an element of this form here, where sigma is just the partition, the marked partition, say, like that. Okay? It is a sum of all transposition where n is appears in the transposition. Okay? So certainly, it is one of these elements which are here. Okay? And this one I can get by just looking at Sn, at Gn. Okay? So now let us go further. Next thing I can do is take Jn squared. So it will be a sum of I, J star plus n minus 1, something like that. Okay? By this I mean the element corresponding to this, or maybe a multiple, maybe the factor, but essentially that's the element I have denoted by this label, which is here. Okay? So you see, by just looking at Jn and Jn squared, we have already found this here. And now, what I can do, I can also multiply Jn by an arbitrary conjugacy class in Sn-1. Okay? So this will be represented by unmarked partitions. Okay? Okay, so suppose I have two. No, because all the transpositions in J, they contain n. It's In times Jn. And if I is equal to J, that gives you the identity, but it's always a free cycle. So now what happens if I multiply such an element which belongs to the center, so there is no n appears here, okay? And I multiply by this here. Then I will get a sum. Okay, so the I which is here, when I do this, I sum over all these elements which are here. The element which is here will appear somewhere in the partition which is here. Okay? And the effect will be that it will, since this element n does not belong to the cycles that are here, it will add 1 to the length of the cycle. So it will be the sum of all the marked partitions obtained by, say, adding okay, so it will be, in this case, it will be this plus. Etc. Okay, so you look at all the cycles of your partition, and for each of one, you obtain an element like that. Okay, and now we have to. We have to see that there is by making all these products, we will find a triangular system. Okay. This means that we will put a degree on the partitions and say that, okay, so here we have obtained partitions which have, so the degree will be the number of elements which are moved, which are non-fixed, the number of non-fixed points. So here we have only 2 non-fixed points, here 3 non-fixed points, and so on. So this gives me a degree that I can put on my permutations. And we will see that each time we will make such products, so we'll make products of such elements, and we will see that we can always find a way to write to obtain an element coming from make a multiplication in which some element will appear together with elements of smaller degree that we can assume by induction that they are already in the algebra. Okay, I don't know if I'm not sure it's clear, but okay. Okay, so how do you do? Well, suppose, for example, okay, so I have to be careful not to say stupid things, but okay, so let's, for example, suppose that we have, so yes, yes, that's exactly. Yes, I can write a triangular equation by putting the right weight on the elements. And I think the right weight is to look at the number of elements which are not fixed by the partition. Okay, so suppose, so as you see, when we multiply by Jn, you obtain, in general, something like that. And if you multiply, say, something like that, so what it will be just the same thing. Okay, like that. Plus, so it's just the first. This means this means that I will look at all multiplication by some transposition of the form In. So 2 things may occur. Either you know, the I which is here appears in some of the things which are here. And then we will add the 2, sorry. Then in this case, we will have to say, for example, I appears here. Then we will have to add the 2 things here, okay? And what remains are the remainder, okay? Or maybe we will have to split these in 2, okay? And then we will have, okay. I'm not very good at reporting exactly what happens on the left, so I think here I have to add 2 more, and then here I think so I have to split this one into 2, so this means that then the largest part will be 3, and maybe I will have something like, okay, if I have a star here, that means that I am just in the group Sn-1. Okay, I may not write it here. Okay, so we just need to find that there is a polynomial system in this way, with a triangular system which expresses all the. Okay, so okay, so let me think. What? Yes, exactly. There is an ordering here. Okay. So we have to make an ordering. Okay, so let me think. So I'm a little lost. I don't remember which order I should take, which is the best order. I think the number of non-fixed points is not really what I would like to have, because it's okay. But okay, let's try. So we have, as I said, if we multiply by Jn such an element, so we have this decomposition which is here, okay. And then, okay, let's start with this one, for example, Jn cube. So it will be something like that, plus, okay. And we will get something like that. If we have to cut, or maybe we will have something like that. Okay. So you see that you can, in this way, you can get, for example, the 4 cycles, okay, which contain this. But of course, we have to. Okay, so let me think. And of course, these are already in our algebra, so we don't. Okay, we don't need to. Okay, we can always. So this means that this one belongs to algebra. So in the
last two summations are all the 2 cycles and all the
yes, exactly. Because it depends. You know, when we multiply. When you look at this element, so this one, of course, the identity I can take out. So if you multiply this one, then either you are adding one, either the I that you are multiplying it doesn't appear here, so you are adding a cycle, or you are breaking the cycle into 2. Okay, there will be one fixed point and a cycle, and the fixed point may be either this one or one of the 2 other points, and in which case you obtain either this one or this one, which is here. Okay?
Why you say that one without?
It is in the center of the. It's a conjugacy class of the symmetry group of order n-1. Okay? Yeah. I'm not sure it will work. Okay. Okay. I think probably the right thing to do is to first prove that you get all the you get all the cycles, okay, by taking the powers of the Jn. That's clear by induction, okay. Wait, not, sorry, that's not clear by induction, because at the next step, so if I multiply a free cycle by this, then I obtain either the 4 cycle, plus then I have to cut the other cycle into 2, and I will have either something like that. So there is 1, 1, 2, 3, 4, 5. Then yes, no, it will always be much smaller. I mean, it will either be this one or this one. Okay. Or it could be, yes. The only thing is that it could be something like that. Okay. So at this point, I have a problem because I need this one. I have already taken care of this one also, but this one I need to take care of. Okay. But this one I can get by multiplying this by this one, okay? So this one will appear inside. Sorry. It's this one, yes. Okay, but this one will appear inside this product, okay, and together with smaller terms. So I think you see how it's going on. I'm not very good at explaining it, but you need to find the right order on the partition. And when I prepared this, I had the wrong order, I think, and then I realized I need to do it differently. So it's not so easy to think about it, but. Yes, it's a filtration. You need to put your filtration. I was thinking just the number of non-fixed points would work, but it's not. It's more complicated than that. So at this point, you have to. Okay, so you see here you have all the 4 cycles. All the 4 cycles. You get the 5 cycles, but then you get a little bit annoyed by this one. But this one was obtained before by this kind of. Multiplication, which is here, okay? So it's not so easy to find what is the right order that you have to put on these things in order to make the recursion work. Okay, so I'm sorry, I have to think that again. Let's say there is something that works. I will show you the exact thing to do next time because I don't want to get into this mess. Yeah. What? Oh, the theorem. I was trying to prove that the Jn and Z of C of Sn minus 1 generate the commutant of this algebra. Okay, and for this I need to find, I gave you a way to index the commutant, a generating system of the commutant by partition which are with some asterisk or maybe no asterisk in them. Okay, all these elements I know linearly generate the whole algebra. So I need to find that these elements belong really to express them as products of elements in this algebra. So if you want polynomials in the Gn with coefficient in the center of Sn minus 1. That's what I'm trying to do with not so much success, unfortunately, because I should have, I thought it was easier than it is, but then when you are in front of the blackboard, you realize it's not, not so obvious it was when you were in front of your piece of paper. So, okay. So maybe I try to give you next time the correct version. Yes. Yes. Yes, that's probably it's the right thing to do, but so that's an exercise. Yes, I guess you're right, because each time you are going to multiply by Jn, you're going to split a cycle into 2. Then the number of cycles is going to grow, but the number of non-fixed points is going to go down. Yeah, I think you're probably right. That's probably the right thing to do. It's better than what it's slightly more complicated than what I thought at this time. So, okay. So let's move on. I try to give you a better proof next time. Okay, so. So what do I do next? Okay, so now that's very interesting because, Jn so they generate the commutant. Okay, well, so what does this mean? This means that when you look at the big matrix that I had before, that gives me my algebra, my matrix algebra, my algebra of the symmetric group. So I know that this matrix is composed of matrices of blocks of this form, like that. Okay, there are lots of blocks. Okay. So now what happens when I look at the subalgebra generated by these elements, C of Sn-1? Okay? When I have a representation, V, which is in general irreducible, say an irreducible representation of Sn-1, Sn, sorry, and then I look at the representation of Sn-1 just obtained by restricting the representation to Sn-1. Okay, so then this space will break into irreducible representation of Sn-1. Okay, with some multiplicity. So I can take a sum. So if you want, each of these spaces here will be, each of these matrices will, if I just look at matrices as a representation of Sn-1, so just the action of Sn-1, it will be broken into smaller pieces. Okay? And each of them will be, there will be the same copy inside each of the small blocks which are here. Okay? But now the point is that the commutant, so let us look into say this block. So I will have a certain number of blocks here. Okay, and in these blocks, some of the irreducible representation of Sn-1 will appear with some multiplicity. Okay, but what I know is that the commutant of the algebra which is generated here is commutative. So this means that all the multiplicities which are here have to be 0 or 1. Okay? Because I know that the commutant of this, so the commutant of the image of Sn-1 into that will be, so the sum of the endomorphism. So it will, its image will be the sum of the non-zero multiplicities, and the commutant of so it will be a sum of algebras of this form. Okay, so maybe over all omega larger than 1. Okay. So, in particular, this algebra will be commutative if and only if all the multiplicities here, the non-zero multiplicities, are equal to 1. Okay? Yes, it is inside the larger algebra. Okay, but here you see you can restrict yourself to this smaller subalgebra of Sn-1, and certainly the commutant inside this is inside this algebra. Okay. Yeah. Here? No. These multiplicies, they depend on V, of course. They depend on V. Here? No, my point is that exactly that if you look at the commutant, so these V omega are irreducible, they appear with some multiplicities, and the commutant is what I said before. If I look at these, the commutant of this representation will be a sum of metric algebras with dimensions given by the multiplicities of the irreducible, non-zero multiplicities, if you want. No. I said in general, if you have a representation, say this is a representation of Sn minus one. If you have any representation of a group G, and the say G on W, and W can be written as a sum of say the irreducible. Okay. Then the commutant of the representation, the algebra generated by the representation is the sum of the endomorphic algebra with non-zero multiplicities here. And the commutant is given by this sum of algebras. Yes. Oh, yes. Because I am looking at this representation as the representation of Sn minus 1. Okay? Initially, it is a representation of Sn. I restrict to Sn minus 1, and I get a sum of a decomposition into a sum of irreducible. Is that clear for? No, here it is a commutant of the image inside this representation, inside this. Okay. I know that in the big algebra, the commutant is generated by this and this, okay? And what I say is that if you look at this picture, you see that in a particular irreducible representation, okay, the commutant will be generated by the image of the center of Sn minus 1 and the Jn. So this means that, what does this mean? This means that all the multiplicities are equal to 1, okay? And also that the Jn will act by, so on each irreducible, so m omega is equal to 0 or 1. So on a non-zero multiplicity, if I have a space which appears with non-zero multiplicity, so if here, then Gn, so the image of Gn by the representation, if you want, the image of Gn makes sense because V is a representation of Sn minus 1. So Gn commutes with the action of Sn minus 1. So it must be a multiple of the identity on each irreducible component, okay, by Schur lemma. So is a multiple of the identity on each component V omega. Okay. Moreover, yes. No, here I use only the fact that Gn commutes. I don't use that. I should have proved better. That's what you mean? I don't use it. I have not used it yet. Now I'm using it. Yes. Sorry, I have used it. Yes. I have already used it to deduce that all the multiplicities are equal to 1. Because the commutant is commutative. And of course, you know, I should add, a matrix algebra is commutative if and only if the matrices have dimension 1. Okay. Okay. Yes. Okay, because you have to look at the you have to look at this picture which is here. Okay, so you have some V which is here, my representation V which is irreducible. Okay, so it appears, for example, here. Okay, what I say is that the commutant of this so inside this representation, the commutant of the action of Sn minus 1. So the action of Sn minus 1, you know, if I draw this larger, it will be given by some, there will be some matrices here, alpha, beta, gamma. Okay. I can decompose it into irreducible, which are here. The question is, are these irreducible of multiplicity more than 1? Can it happen? It cannot happen because if there were some multiplicity higher than 1, then, for example, I would have also always the same alpha, which would appear here by taking the right basis, then I would have larger commutant, a 2x2 matrix commutant. Okay? And this is not possible because I know that inside this very large algebra, inside the very large algebra, the commutant is commutative. Okay, so that means that all the multiplicities have to be equal to 1 here. Okay? Not only all the multiplicities have to be equal to 1, but so I know that the commutant on each irreducible representation, the commutant has to act by a scalar, by Schur lemma. Okay? And moreover, the eigenvalues why do they have to be distinct? Is it so obvious? Okay, so Gn is a multiple of the identity, so it has an eigenvalue on each NA component. Because, okay, well, doesn't seem so obvious now, but okay. Anyhow, no, it has to be irreducible because if not, you cannot. For example, you could take twice the same representation, the sum of two identical representations of Sn, and then there would be a commutant which is larger. Now you need Schur lemma for Sn that the algebra generated by Sn, by the Sn is everything. If it's not true, then you will have more things in the commutant than you want to. Yes. You need that it be, because if I have several, if I have things like that, then I have a larger commutant inside, which come from the others. So I cannot do. Okay. So let us. Okay. So maybe. I think, okay, sorry. So I didn't have I didn't have time to do what I wanted to do because maybe I didn't prepare enough, and then so I was a bit mixed up at some point. But okay, so I just tell you in a few minutes what we are going to do. We are going to look at the sequence of operators. And I will add G1, which is equal to 0. Because it's convenient to have. And what we know is that in any irreducible representation of Sn, these operators can be diagonalized simultaneously. Okay? There exists a basis of simultaneous eigenvectors. And correspondingly, a sequence, say A1, A2, I think AN, a sequence of eigenvalues, okay? So what I will do is I will use this sequence to index the vectors of the representation. And I will show you that, one can characterize in a geometric way all sequences which appear in this way. It will not be an arbitrary sequence of numbers. We will see that they will be all integers, and they will satisfy some conditions. And using that, from these sequences, we will be able to build Young diagrams. We will be able to build Young diagrams and Young tableaus, standard Young tableaus using these sequences. And this will use really the algebra generated by the JN. Okay, but then, okay. So I need to do that next time, okay? I thought it would take a minute.